We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
I feel the liftoff. The clock has started. Roger. Godspeed, John Glenn.
Roger, 0G, and I feel fine.
This is a new and strange environment at first. This suddenly finding yourself in orbit.
We have a liftoff, 32 minutes past the hour. Liftoff on Apollo 11.
Houston, Tranquility Base here. The Eagle has landed. I'm going to step off the limb now. That's one small step for man, one giant leap for mankind.
Okay, Houston, we've had a problem here. This is Houston. Say again, please. Houston, we've had a problem.
Welcome home, Columbia. Beautiful, beautiful.
Discovery, go at throttle up.
Discovery, Roger, go at throttle up.
Nose gear touchdown. Having fired the imagination of a generation, a ship like no other, its place in history secured, the space shuttle pulls into port for the last time. Its voyage at an end.
Hello and welcome. This is Michael Annis, and you're listening to episode 1 of the Space Rocket History Podcast. And now, ancient rocketry standing on the shoulders of giants. From our small world, we have gazed upon the cosmic ocean for thousands of years. Ancient astronomers observed points of light that appeared to move among the stars. They called these objects planets, meaning wanderers, and named them after Roman deities: Jupiter, Mars, Mercury, Venus, and Saturn. The stargazers also observed comets with sparkling tails and meteors, or shooting stars apparently falling from the sky. Often the early rocket pioneers are lost in the shadow of time. The space rockets of today are the result of more than 2,000 years of invention, experimentation, and discovery. The foundations for modern rocketry were laid first by observation and inspiration, and then by methodical research. The first steps toward a scientific view of the universe were taken in Babylonia and Egypt 5,000 years ago. As early as 3000 BC, Babylonian astronomers were making methodical observations of the skies. By 2000 BC, they had fitted the planets to a zodiac system. By 1000 BC, they were keeping records of movements of the brighter planets, as well as the sun and the moon. The ancient Greeks built on the Babylonian and Egyptian astronomers' work. Thales of Miletus, the father of Greek science, mathematics, and philosophy, was able to accurately predict a solar eclipse on May 20th, 585 BC. The eclipse so frightened the armies of Media and Lydia that they negotiated peace with the Greeks. One of the first devices to successfully employ the principles essential to rocket flight was a wooden bird, invented by a Greek philosopher, mathematician, and astronomer called Archytas. Somewhere around the year 400 BC, Archytas mystified and amused the citizens of Tarentum by flying a pigeon made of wood. Escaping steam propelled the bird suspended on wires. The pigeon used the action-reaction principle, which was not stated as scientific law until the 17th century. About 300 years after the pigeon, another Greek, Hero of Alexandria, invented a similar rocket-like device. Though not a rocket, the main principle behind rocket propulsion was employed in a steam engine device called an aeolipile. An aeolipile is essentially a steam reaction turbine. In modern times, it is often referred to as a hero's ball. This ingenious device was described in detail in Heron's book Pneumatica. Hero mounted a sphere on top of a water kettle. A fire below the kettle turned the water into steam, and the gas traveled through pipes to the sphere. Two L-shaped tubes on opposite sides of the sphere allowed the gas to escape, and in doing so gave a thrust to the sphere that caused it to rotate. If you're having trouble visualizing this, don't worry. I have a picture of the Hero's Ball and other inventions that I will mention on my website at spacerockethistory.com. Just when the first true rockets appeared is unclear. Stories of early rocket-like devices appeared sporadically through the historical records of various cultures. Perhaps the first true rockets were accidents. In the 1st century A.D., the Chinese reportedly had a simple form of gunpowder made from saltpeter, sulfur, and charcoal dust. To create explosions during religious festivals, they filled bamboo tubes with a mixture and tossed them into the fire. Perhaps some of those tubes failed to explode and instead skittered out of the fire, propelled by the gases and sparks produced by the burning gunpowder. At some point, the Chinese attached bamboo tubes to arrows and launched them with bows. Soon they discovered that these gun-powered tubes could launch themselves just by the power produced from the escaping gas. The true rocket was born. The date reporting the first use of true rockets was 1232 A.D. At this time, Chinese and the Mongols were at war with each other. During the Battle of Kaikung, the Chinese repelled the Mongol invaders by a barrage of arrows of flying fire. These fire arrows were a simple form of a solid propellant rocket. A tube, capped at one end, contained gunpowder. The other end was left open and the tube was attached to a long stick. When the powder was ignited, the rapid burning produced fire, smoke, and gas that escaped out the open end and produced a thrust. The stick acted as a simple guidance system that kept the rocket headed in one general direction as it flew through the air. It's not clear how effective these arrows of flying fire were as weapons of destruction, but their psychological effect on the Mongols must have been formidable. Following the Battle of Kaikung, the Mongols produced rockets of their own and may have been responsible for the spread of rockets to Europe. All through the 13th and 15th centuries, there were reports of many rocket experiments. In England, a monk called Roger Bacon wrote about gunpowder in his epistle, The Secret Works of Art and Nature. In his epistle, Roger wrote, "We can, with saltpeter and other substances, compose artificially a fire that can be launched over long distances. By only using a very small quantity of this material, much light can be created, accompanied by a horrible fracas. It is possible with it to destroy a town or an army." End quote. Roger Bacon is credited with developing improved gunpowder formulas that greatly increased the mixture's power and rocket's range. In France, Jean Froissart found that more accurate flights could be achieved by launching rockets through tubes. Froissart's idea was the forerunner of the modern bazooka. In 1420, Ones de Fontana of Italy designed a surface-running rocket-powered torpedo for setting enemy ships on fire. For centuries to come, rockets competed with cannons as the weapon of choice for wars. Each technological development moved one or the other system into or out of favor. Cannons were more accurate, rockets could be fired more quickly, breech-loading cannons speeded up the firing, rocket fins increased the accuracy, cannons had greater range, then rockets had greater range, and so on. Nearly all the uses up to this time were for warfare or fireworks, but there is an interesting old Chinese legend that reported the use of rockets as a means of transportation. With the help of many assistants, a lesser-known Chinese stargazer and a local official named Wan Hu assembled a rocket-powered flying chair. Attached to the chair were two large kites, and fixed to the kites were 47 fire arrow rockets. On the day of the flight, Wan Hu sat himself on the chair and gave the command to light the rockets. 47 rocket assistants, each armed with torches, rushed forward to light the fuses. In a moment there was a tremendous roar, accompanied by billowing clouds of smoke. When the smoke cleared, Wan Hu and his flying chair were gone. No one knows for sure what happened to Wan Hu, but it is probable that Wan Hu and his chair were blown to pieces. Fire arrows were as apt to explode as to fly. Regardless of the actual end, Wan Hu had the right idea: use rockets to travel into space. In 1591, German fireworks maker Johann Smeatlap invented the step rocket, a multi-stage vehicle for lifting fireworks to higher altitudes. A large skyrocket, the first stage, carried a smaller skyrocket, the second stage. When the large rocket burned out, the smaller one continued to a higher altitude before showering the sky with glowing cinders. Smeatlap's idea is basic to all rockets of today that go into outer space. Kazimierz Siemianowicz, a Polish-Lithuanian commander in the Polish Royal Artillery, also contributed to multi-staging. In 1650, he published his manuscript called Artis Magnae Artilleriae. The manuscript included his design for multi-stage rockets that became fundamental for rockets heading into space. He also proposed batteries for military rocket launching and delta-wing stabilizers to replace the guiding rods currently in use with military rockets. In the 17th century, Italian astronomer and mathematician Galileo Galilei challenged old beliefs relating to mass and gravity. He proved that an object in motion does not need the continuous application of force to keep moving. He called this property of matter, which causes it to resist changes in velocity, inertia. Inertia is one of the fundamental properties that Isaac Newton would later incorporate into his laws of motion. During the latter part of the 17th century, the scientific foundations for modern rocketry were laid by the great English scientist Sir Isaac Newton. In 1687, Newton's book, Principia, was published. In his book, Newton organized his understanding of physical motion into 3 specific laws. The laws explain how rockets work and why they're able to work in the vacuum of outer space. Here now, in simple form, are Newton's laws of motion. Law number 1. Objects at rest will stay at rest, and objects in motion will stay in motion in a straight line unless acted upon by an unbalanced force. In rocket flight, forces become balanced and unbalanced all the time. A rocket on a launch pad is balanced. The surface of the pad pushes the rocket up while gravity tries to pull it down. As the engines are ignited, the thrust from the rocket unbalances the forces, and the rocket travels upward. Later, when the rocket runs out of fuel, it slows down, stops at the highest point of its flight, and then falls back to Earth. Objects in space also react to forces. A spacecraft moving through the solar system is in constant motion. The spacecraft will travel in a straight line if the forces on it are in balance. This happens only when the spacecraft is very far from any large gravity source, such as Earth or other planets and their moons. If a spacecraft comes near a large body in space, the gravity of that body will unbalance the forces and curve the path of the spacecraft. This happens in particular when a satellite is sent by a rocket on a path that is parallel to the Earth's surface. If the rocket shoots the spacecraft fast enough, the spacecraft will orbit Earth. As long as another unbalanced force does not slow the spacecraft, it will orbit Earth forever. Newton's law restated: if an object such as a rocket is at rest, it takes an unbalanced force to make it move. If the object is already moving, it takes an unbalanced force to stop it, change its direction from a straight line path, or alter its speed. That was law number 1. Newton's law number 2. force is equal to mass times acceleration. Let's apply this principle to a rocket. The mass is the sum of the mass of the rocket and the mass of the propellant ejected out of the rocket engine. Force is the pressure created by the controlled explosion taking place in the rocket's engine. That pressure accelerates the gas one way and the rocket the other. By far, the largest part of the rocket's mass is its propellants, but that amount constantly decreases as the engine fires. That means that the rocket's mass gets smaller during flight. In order for the left side of the equation, force, to remain in balance with the right side, which is mass times acceleration, the acceleration of the rocket has to increase as its mass decreases. That is why a rocket starts moving slowly and goes faster and faster as it climbs into space. Newton's third law. For every action, there is always an opposite and equal reaction. For example, if you ever stepped off a small boat that is not properly tied to a pier, you will know exactly what this law means. A rocket can lift off from a launch pad only when it expels gas out of its engine. The rocket pushes on the gas, and the gas in turn pushes on the rocket. The whole process is very similar to riding a skateboard. Imagine that a skateboard and a rider are in the state of rest, not moving. Now, suppose the rider jumps off the skateboard. In Newton's third law, the jumping is called an action. The skateboard responds to that action by traveling some distance in the opposite direction. The skateboard's opposite motion is called a reaction. With rockets, the action is the expelling of the gas out of the engine. The reaction is the movement of the rocket in the opposite direction. To enable a rocket to lift off from the launch pad, the action of thrust from the engine must be greater than the mass of the rocket. In space, however, even tiny thrust will cause the rocket to change direction. One of the most commonly asked questions about rockets is how they can work in space where there is no air for them to push against. The answer to this question comes from the third law. Imagine the skateboard again. On the ground, the only part air plays in the motion of the rider and the skateboard is to slow them down. Moving through air causes friction, or as scientists call it, drag. The surrounding air impedes the action-reaction. As a result, rockets actually work better in space than they do in the air. As the exhaust gas leaves the rocket engine, it must push away the surrounding air. This uses up some of the energy of the rocket. In space, the exhaust gases can escape freely. Okay, if I lost you in all those technical explanations, let me restate it with a rocket example. An unbalanced force must be exerted for a rocket to lift off from a launch pad, or for a craft in space to change speed or direction. That is Newton's first law. The amount of thrust, force, produced by the rocket engine will be determined by the mass of the rocket's fuel that is burned and how fast the gas escapes the rocket. That is Newton's second law. The reaction or motion of the rocket is equal to and in opposite direction of the action or thrust from the engine. That is Newton's third law. By applying Newton's laws of motion, rocketeers have been able to design, construct, and operate the modern giant rockets of the 20th and 21st century. This is what Newton thought of his accomplishments. I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore, and diverting myself now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me. If I have seen further, it is only by standing on the shoulders of giants. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange donate button or the Patreon link. Thanks.